Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. Well, you're probably watching this video because you had a problem here that involved taking permanganate polyatomic ion and reacting it with the chloride ion and wanted to find out how to balance this using oxidation and reduction. You've already figured out, I hope, how to come up with oxidation numbers, and now we're going to try and apply them to see how this reaction would occur. But let's take a little detour to the potassium permanganate first. That's the common version of this, where they combine the permanganate polyatomic ion with potassium, produces a blackish, purplish solid. And of course, if it's a potassium compound, dissolves beautifully and makes this just fantastic purple color when it dissolves. You just need the smallest speck of this to produce a really, really dark solution. If you've ever worked with potassium permanganate, you will have found out that some of it has gotten on your clothes, your lab jacket, and it's going to stain it. This will react with the cellulose and make sort of a brownish stain. I did a quick search on videos that involve removing potassium permanganate stains. It's that common. In fact, here you can see we've had video that has 37,000 views, and it's making up a solution that will react with the potassium permanganate to make a clear solution. Let's go to the problem. That's why you're here, to find out how to balance this. Well, we've got the reaction in here. I've got these dots saying, okay, this is where I want the coefficients. In a college class, they would expect you to do all the balancing, including the acid. But for AP, the big idea is to be able to figure out the balancing of the substances that oxidize and reduce. Well, first thing, let's get the oxidation numbers. And these numbers are dependent upon a couple of things. One, of course, if it's an ion, and if it's an ion, the oxidation number will be the charge of that ion. Now, here's the oxidation number for chloride, which is a -1. Because it's a number, we'll put the sign in front of it. Our hydrogen has a +1, and one of our rules is a oxidation number of an element to be the charge of that specific element. Or, if it has no charge, if it's an element, like here, chlorine, by definition have an oxidation number of 0. Oh, here's another easy one, a +2. So we're going to be getting all these oxidation numbers, and these are easier ones because they're dependent on just the charge of the element or an element not having a charge. So logically it's 0. Now we've got some other molecules here that we don't know the charges or the oxidation numbers of. There's one set of rules that if you have oxygen in a compound, not as an element, it will have a charge of -2, almost always, unless it's combined with a fluorine. Excuse me, -2. In fact, this is wrong. This says +1. That's the charge for our hydrogen. The oxygen here will have a -2. In fact, here's another oxygen, and it has the -2, and I should have that -2 on this. In fact, let me fix that right now, which is right there. A -2 oxygen in a compound, unless it's a peroxide or combined with fluorine, is a -2. Hydrogen will, in a compound, will always be +1. And here I can move this over there, and that'll take care of oxidation numbers of the hydrogens and oxygens. So let's see, we've got the oxygen taken care of, fixed now. We've got these ions. The only left over here is manganese, and I saved that for last because transition metals typically will have all sorts of oxidation numbers. They're hard to predict, and unless you've got its name with its charge, then you're going to have to do a little bit of computing. And the computing here is going to involve what it's combined with. It's combined with 4 oxygens, and we know the oxidation number of those oxygens. Also, we note that this entire compound has a charge of -1. The rule is when you've got a polyatomic ion, the oxidation numbers will add up to what the charge is. So we have 4 -2s. That's going to be a -8. 4 times -2 is -8. Our manganese, we only have 1 of, so it's going to have to add up to the -8 to produce a -1. Okay, I'm not going to pull my calculator out for that. That's going to be a +7. So there is our permanganate manganese oxidation number. We've got the oxidation numbers of everybody here. Every single element, we've got the oxidation number of one of them. Sometimes we have to go down here to find out the total oxidation number, do some calculating, but we want to end up having the oxidation number of every single element because we want to see if there's any changes. Now, if you have an element like this, chlorine, and it's not an element on the other side, which it can't be because we need a change, we know that here's a change in oxidation number from -1 to 0. That's going to be one of the substances we have to look for. In fact, if it's a -1 to 0, that means the number is going up the number line, which is oxidation. Oxidation is loss of electrons. Hope you remember that. So we know right away that our chloride is going to be something we're going to be interested in. We're going to be interested in the chloride because it goes from a -1 to a 0. We have this -1 and we have this 0. There's a change. And we want to see if there's any other changes. That's what's going to be used for balancing the reaction. Well, I look at my hydrogen +1, +1, oxygen's -2, -2. Well, that leaves our manganese. And the reason you find permanganate very often in a chem lab is because its oxidation number does change. You can have it do something for you. In a chem lab, you want to make changes. Well, permanganate is excellent for it because, look, it goes from a +7 to a +2. It reduces. It ends up gaining minuses. That means that it is reducing, so it's an oxidizing agent. In fact, it's pretty dangerous. You have to watch out where you store it, and don't store it with anything that it can grab electrons from. Here, we'll look at our manganese 7 that we start off with. It has a charge of +7 if you imagine it all by itself, and it changes into manganese +2. Here, I put the +2. We've got our two reactions, and that's what you always have in an oxidation reduction. We've got one number going down, reducing, gaining minuses, gaining electron, reduction, reducing its number here. And we have another substance that has to be oxidizing, giving those electrons away. Manganese can't get these electrons from thin air. It doesn't manufacture them. It's got to take them from the chlorine. So whenever there's a reduction, there's also an oxidation, and they have to be equal. There is a trick question once I saw somebody ask us, what happens more often, oxidation or reduction? Well, they both have to happen equally. You just don't create electrons, you move them around. There is an exception for that if you've got a cosmic ray, but then you get anti-electrons too. We're going to have to gain electrons. Well, how many electrons are we going to gain? +7 to +2, well, that's 5. We're gaining 5 electrons. We're adding these 5 minuses to this +7 to get a +2. The charges will be the same on reactants and product side. A -5 at a +7 gives us a +2. Charges are the same. Now, the chloride's a bit weird here, and that's what makes this problem difficult. Chlorine is diatomic, and you can't do anything about that. I mean, this subscript 2 you can't change, so we'll have to put a coefficient of 2. We're forced to do that for the chloride because the chlorine is diatomic. So we have to have that coefficient of 2. Now, if it is losing electrons, then that electron is sort of kicked out. And here I've got 2 -1s, -2. So we have to get rid of 2 electrons. Now this is the tough part. If you've gotten this far, you're in great shape. We've got 5 electrons and 2 electrons, and you heard me ranting before saying that electrons gained have to equal electrons lost. So I'm going to go to this next step. We're going to deal with this. We have 5 electrons gained, reduction, going downhill. We've got 2 electrons being kicked out. They've got to be equal. You can't have a different amount of them, so that's why I put the parentheses. Of course, 2 and 5, how am I going to make things equal with a set of whole number coefficients? If I multiply this reaction by 2, I get 10 electrons. If I multiply this reaction by 5, I get 10 electrons. That takes care of things. My reduction equals my oxidation. This is how the reaction is going to occur. You will have 2 times as many manganeses compared to 5 of our chlorines. That's going to be our ratio. In fact, that's the heart of balancing this reaction. I'm going to have a 5 for my chlorine and a 2 for my manganese. This is a must. This determines what's going to happen. 2 manganeses, and I've shown 10 chlorides. I have to multiply this 5 times 2 because of this diatomic chlorine complication. In fact, remember when we started chemistry, the first thing I said, you're going to have to know your diatomic substances, and here they are. This is the way our chlorine is. We're going to produce this yellowish gas, and this manganese is going to dissolve, make a little pink solution with the chlorides. And that now is what we're going to put into our balanced reaction. We know 2 manganeses. 2 manganeses. Yep, balanced reaction. We're answering this question. How many chlorines? Well, 5 diatomic chlorines and 10 chloride ions, because we've got these monatomic chloride ions. In this reaction, I put in the hydrogen ions because on the AP exam, they're not going to have you worry about the acid-water part. In the college class, they have you figure out the acid part and the water part. But of course, if there's 16 H pluses, you're going to have 8 waters. Now, you can tell if this is done right. If the charges of the reactants equal the charges of the products. So let's find the charges of our reactants. 2 negative 2s, 10 chlorides. That's a total of 2 negative 1s. That's a negative 2. Therefore, with 16 H pluses, we have a net charge of 4 plus. Double check. 2 negative 1s. 10 more gives us a negative 12, but we have 16 H pluses here. So our total charge that we have of our reactants are going to be plus 4. Well, if we have a plus 4 here, that means we need to have a plus 4 here. 2 times plus 2, plus 4, no other charges. All is well with the world. You know you've done it right if the charges of the reactants equal the charges of the products. And we've got this right. It took a while. These things are going to be time intensive, but typically on an AP exam, just getting to the part where you know that there are 2 manganeses for every 10 chloride ions, that is all you need to know. This rest of this stuff would be extras and unlikely, but I wanted to go through them to show how everything worked. So we now know how to use oxidation numbers, which we started off with here, to figure out half reactions, to figure out the ratios in which our reactants will work. I mean, we now know, using this little number system, what coefficients to put in. And if you're going to mix this up to do a perfect reaction, we know the coefficients that we'll need, the stoichiometry of the problem. Okay, Redox, love it.